Hello, my science lovers. So, my computer wanted to update like right away. And I'm like, okay, silly computer wanted to update right as I'm trying to get my stuff done. So, here we go. Um, so, today we are talking about spectroscopy, which will be pretty cool. And I'm 20 minutes late. So, woohoo on that, right? And so this was the topic that won last time. So let me go through and see if we're live everywhere. I know I've been I've had this going, my live stream all the time with my 24/7 one, but this is not a 24/7 one. This is an actual one that I'm doing right now. So yes, I'm on Facebook, so that's working. Yay for Facebook. I'm on there. Let me see if I'm on Periscope, wherever that app is. Oh. Hello everyone. Hello, how are you? Yep, I'm on Periscope and I should be on YouTube. So let me check that out and see what's going on with that. Hopefully I've got that going on. Yes, and I am on live on YouTube with Spectroscopy. Yay! Greetings. Hello. So this was the episode. This was the topic that won this particular poll. So spectroscopy. We are going to talk about UV vis, infrared, and I'm going to touch a little bit on mass spec, which has nothing to do with electromagnetic radiation. So let's go ahead and get started. Okay. So, production value. Yeah, that's been my intro for a while. Peter, aka Gonna Go For It, made that for me. He's made all of my intros and outros. Also, coming up, January 24th, the very first episode of This Week in BS, featuring the lovely Katie from Pathos. So we will be talking the latest and greatest in bad science. Also coming up this month, I believe it is not next weekend, but the following weekend, is the newest episode of Spirited Science featuring Andy DeWitt as my new co-host. We will be in New Orleans with Monty from Hannibal and Monty's show. It's got a dirty word before it, it's like I'm trying to be like not, but it says Hannibal Monty's shit show. Shh. Okay. So Monty, I have a weekly spot on their show where I talk about something regarding sciencey stuff. I talked a bit about metric. Talked a bit about metric when we were talking about film. So they're going to use the new metric unit, RARs and laws, in order to determine how great a film is. So there you go. So yes, Spirited Science is coming back. We will be talking about the first licensed pharmacist as well as eugenics that were used in Louisiana with Monty from Hannibal and Monty's Shit Show and my new co-host Andy DeWitt. So yay! So today, you guys picked spectroscopy. This is a pretty hefty topic, but it's not so difficult in theory or in how the instruments are put together. So I'm going to use a little bit of math. I'm going to talk a little bit about different things associated with UV vis spec, infrared, and I'm going to touch a little bit on mass spectroscopy. So this show will be measured in megalols. That's correct. All right, so what am I going to cover? Well, you could spend years talking about spectroscopy and all of the different ways that you use, especially ones associated with the electromagnetic spectrum. So we're going to talk about the most used types of spectroscopy. We're going to talk about how it works. We're going to talk a little bit about how it's different from mass spec, which is something else entirely. So many people get confused when they see spectroscopy and they think mass spec. They think it's the same thing, but it's not. It's very different. But you can use both together to kind of help determine what's in your solution based on how it breaks apart. So that's kind of how mass spec is. We're going to talk about that. So for spectroscopy, it's electromagnetic spectrum based, all right? So if you watched my show on light, on photons, I talk a lot about the electromagnetic spectrum. So if you get kind of lost a little bit, go back and check out that particular episode, and that will help you out a little bit when we're talking about spectroscopy. It looks at absorption and emission. So what exactly does that mean? All right, so what we got here we've got the dark side of the moon, you know, kind of like, we got a prism, all right? So what is essentially measured when we're dealing with spectroscopy? It measures particularly elements and compounds. Well, elements and compounds absorb light and they release light. So spectroscopy, you can measure what wavelengths are absorbed. You can also measure what wavelengths are emitted. So that's essentially what we're doing. Hello, science lovers. Hello. The highest end of the DC to daylight spectrum, as us ham operators like to call it. So yes. So we're going to be talking about how it is that they measure these things. So that's essentially what spectroscopy is. Oh, hello, Brian. Hello, everyone. So let's talk a bit about this. Let me see. We got some heavy stuff. We got some heavy lifting to do today, guys, because it can be a bit scary. All right. And I don't want you guys to freak out, you know, because chemistry and math and physics fear is real. And sometimes people get scared when you get involved with math and you're talking about different things. So I'm not going to lose you. We're going to go through this together to where we don't freak out. All right. So just to kind of recap, if you're not familiar with atomic absorbance, essentially what it is, specific wavelengths of light. And that's what we're talking about when we're talking about absorption. The UV visible spectrum excite electrons as they hit elements and compounds. Now, only highly specific wavelengths of light excite classes of compounds. So, because these wavelengths are so specific to these compounds, they make for a great way to detect them in solutions to determine whether or not they're there. All right? So, for example, proteins tend to absorb at the 280 nanometer wavelength. That's because of what they have are called aromatic rings. So those aromatic rings are all over freaking proteins because, you know, to be honest, proteins are huge. So they have a lot of their structures are this way. Genetic code tends to hit at 260 nanometer wavelength. This is largely due, again, to their structures. So their structures, their chemical structures, dictate which wavelengths actually are absorbed. Because remember, elements only respond to highly specific wavelengths of light. So when you put them together, it makes kind of a neat little spectral line pattern. And so it's important to note that with this, the type of bond involved with these compounds determines what wavelength it absorbs. All right, so basic chemistry, you have single bonds, you have double bonds, you have triple bonds. Well, the type of bond is really, really important because when you're dealing with UV and visible spectrum, you're mostly exciting the electrons. And so where do you find electrons? In bonds. Now, double bonds that are conjugated. Now, conjugated might be a new word for some people, but all that means is just every other bond is a double bond. They tend to absorb light in the UV spectrum. the more that you have a conjugated system within a compound, the stronger the presence it is in the UV spectrum. Thus, we use sunscreen, okay? Because because UV light is associated with cancer. Yeah, well, our melanin has a conjugated system, but it can only withstand so much UV radiation. All right, so our natural proteins in our body that kind of try to absorb that UV radiation to where it doesn't hurt our skin, well, sometimes that's not enough for us. So we have to put on sunscreen because sunscreen has a conjugated system, and therefore it absorbs a lot of that UV light and you don't get sunburned. Well, the same thing happens in spectroscopy. What about Bond, James Bond? Woo! I just dropped my mouse. That's why live streaming is exciting, because you mess up, Bond, James Bond. Pi bond versus sigma bond is absolutely right. Single bonds tend to be sigma bonds. Double bonds tend to involve pi bonds. So that's just something to kind of keep in mind. You guys are so smart. Now let's talk about the difference. Hey, Andy. Let's talk about the difference between infrared versus UV vis. UV being UV rays and vis being visible spectrum. Well, they're different in that infrared measures vibrations, not absorption. Okay, because infrared does different things than UV vis does to atoms, right? Now, if you remember from my photon talk, and if you haven't checked that out, it would help a bit with this particular talk. It wasn't that funny. Oh my goodness, guys. All right. All right, so infrared waves kind of give off heat. Now, this is due to causing the atoms to vibrate. So within a particular compound, they're going to shake things up a bit and vibrate, right? Now, infrared spectroscopy measures these vibrations at particular wavelengths. So you can blast with something, and if it's shaking at a wavelength, then you're like, okay, what shakes at this wavelength? This compound does. Fantastic. Well, also this one does too. Huh. So you get, at least can narrow it down a bit, Now, certain compounds show up in the infrared spectrum. One particular use for infrared, IR, that's another shortened version of that, is nanoparticle tech. And I talked about that on this channel too, because I did research in that. Now, I gave this talk last month, and you can check it out on my channel about nanoparticle technology. But the thing that's really awesome about it is this. Metal-based nanoparticles have strong infrared signals. So you can bind proteins to nanoparticles to enhance an IR signal for their presence. Now, this is particularly handy in that you can specialize and customize nanoparticles to target particularly bad cells like cancer in a solution with very, very high sensitivity and accuracy. Now, why would we want to do that, ScientistMel? Don't we have cancer tests right now? Yes, but you have to have a high concentration of cancer cells in order to find those particular, in order to definitively show that there's cancer there. If you use nanotech, you can say, okay, this particular type of cancer, the antibody for that is CD64. We're going to take these nanoparticles, coat them with CD64 antibodies, and then we're going to take a solution from this, take a blood sample from this patient, and then we're going to test their blood sample to see if they have even one cancer cell in there. That's possible with nanoparticle technology. And it shows up on infrared. Your chemistry professor was obsessed with gold nanoparticles in medieval glass making. Yes, it changes colors. That's actually, one of my professors talked about the same thing. It's called plasmon resonance. And so because of the plasmon resonance, they're able to attach, and you can take these nanoparticles, attach them to different cancer cells. And because of that particular effect, it shows up on the IR spectrum. And so the stronger the peak, the higher the vibrations, the more likely you are to have that there, and you can actually determine that. So we're going to look at a few specs in just a bit. I'll focus mostly on UV vis, and we'll check out with what box diagrams look like of the instruments for both like spectrometers as well as mass spec. But first, let's talk about something that everybody loves, math, right? You guys love math, don't you? There's so much math. Oh no, not math. People are like, not the math, no. So, here we go. Beer's Law. This has nothing to do at all with the tasty beverage so many of my viewers enjoy. So, the extinction coefficient is not a blackout number. It's not like you can determine. You know, funny way to look at this. I was talking to this at one of my other jobs. Right. Some people didn't know what Beer's Law was. I'm like, well, you know what? They probably thought it was have to do with the tasty beverage, and then the extinction coefficient is where you black out, right? You know, and the concentration has to do with how many beers you actually had, right? You know, and the path length is how far you are to your door, you know, and then the absorbance is hitting the ground, right? Right? That's not Beer's Law. That's not Beer's Law. What is Beer's Law? Okay, it's absorbance. Okay, so we've been talking about how compounds absorb light. All right, so the amount that's absorbed is important. That's absorbance, right? Your path length is how far the light is traveling. So when you like, your path length is usually determined by the size of your cuvette in your sample. So it tends to be 1 centimeter. So that makes that number 1, which is easy. B is almost always 1. You just put a 1 there. That's easy. Your extinction coefficient. Well, you even said not the math when I suggested statistical physics. That's true. I did say that. All right. Your extinction coefficient is a set number of how well a compound absorbs light. And you know what? You can look that up. It's usually is a predetermined number, unless you're in any kind of research where you're working with new compounds and proteins. If you're dealing with proteins, like recombinant proteins, if you know the amino acid sequence, you should be able to determine the extinction coefficient. So you can still mathematically determine it. It's just a pain in the butt if you have to do that. But usually there's plenty of information on the internet about any given particular protein or any particular molecule. They do have these numbers pretty well set. And then this determines your concentration. So your strength of your absorbance, so your absorbance number is equal to how well it absorbs the light. That's the extinction coefficient, how long the path is, and how much is there. Okay, so that makes sense. You know, if the path is like, 1, then, how well it absorbs it plays a role, and how much is actually in the solution is going to determine your absorbance number and how much it absorbs that light, right? You got that? It's cool. That's in RF country, not like, I don't know, UV vis. UV vis, I always use 1 centimeter cuvettes, for mine, because I like the math to be pretty easy there. So let's take a hypothetical situation. You guys want to be scientists with me for a minute? How are we going to do this? All right. So remember when I said that proteins hit at 280 nanometer wavelengths, and genetic code hits about 260 nanometers. Okay, they're pretty close, but it's still good enough distinction. Let's say that you have a solution that you're trying to determine the concentration of protein and DNA within it. All right, so you go over to a UV vis spec instrument, and you're like, all right, and then you place your sample in a 1 centimeter cuvette, okay, and then you put it in, and then you close the lid, and you push the button. You're going to get a reading. That's your absorbance rating, your number. And then you're going to get a graph, a type of curve. Oh, watch it, Mel, Mythbusters before work. Woohoo! Now, let's see what these type of curves would look like. All right? So I'm going to show you here what these kind of curves should look like. So I'm going to hop you over to my big monitor. All right, so you should get something that looks like this. All right, if your solution has any kind of genetic code in it, now the nucleic acid is black, okay? So this is our nucleic acid, red is going to be our protein. All right, so if your solution doesn't have any protein in it, but it has nucleic acids, you should get a reading. You should get like, hey, look, it's at 260 nanometers. No, notice nothing is really here. You might, well, you do have something. I will say you have something at about 0.2 absorbance, but it's not substantial, is it? You have mostly genetic material within this solution and a pretty high absorbance, you know. So here we go, 260. All right, now let's say that you end up getting this. All right, so we've got something that's hitting around 260, nucleic acid plus protein, and then the nucleic acid by itself. Now, here's something that's pretty interesting. Sometimes you can have them kind of blend together like this, all right? That means you've got this blending in of your nucleic acid and your protein. So there's a different type of math for this. And you can actually run at a particular spec, one spec at 260, all right? And so if you want to determine how much of your protein is there, you'll just take your concentration at 260 and you'll subtract that from whatever your number is here, and that'll kind of give you your protein, which is kind of interesting on that. The live chat isn't going well. Oh no. A nano cuvette with Beer's Law. Oh my goodness. If your path length is, okay. So this is pretty interesting. Somebody's talking about a nano cuvette. There's something called the nano drop. Okay. There's something called the nano drop. And it's pretty useful. It's a type of instrument. But you can't have a heavily concentrated type of sample. I mean, it's kind of delicate. You don't want to dilute it any further. Now, sometimes, and I'm going to talk about dilutions here in a minute. Now, if you've got what's called a nano drop, your path length is so freaking tiny. The last thing you want to do is dilute your sample because you're using like a few microliters. It's like a drop. So you don't have like a really nice tall cuvette with your solution in there. So if you're using a nano drop, your path length is just ridiculously small. You just put a little drop on the thing and you close it and it blasts it with light. It literally, if I have a pen around here, if you have a pen at home, like the top of an ink pen, you put a drop on that. That's a nano drop. It's nice, especially if you're dealing with industry, to where you're trying to sell a product where you're making lots of proteins and you don't want to waste any particular proteins on testing. So you use a nano drop, you don't have to dilute, you don't have to worry about contaminating your sample. You just literally take it out of here, close it up, press a button. Oh, look, there's a spec. It hits at 280. We got protein. Woo! You know, so it allows you to also be able to calculate the concentration that you have, like in your final product. Nano drops are pretty freaking awesome in that way. So that way, even though the path length is ridiculously small, never dilute your sample for a nano drop. That's a very bad idea. Andy's still recuperating from movie night. Oh, goodness. I think movie night was, you ruined the chat, don't worry. So that's an interesting, so when you're talking about path lengths, that's extremely important, because if you dilute your solution too much, especially when your path length is ridiculously tiny, you're not going to get accurate numbers. So the math is pretty important. So, math! Woo! Oh my goodness. All right. So here's the question is, how do we determine concentration using Beer's law with absorbance numbers? So you notice, like on that particular graph, we had absorbance on the y-axis. We had wavelength on the x-axis. Now what you do is you get your absorption number, you plug that into your equation, that's the A, right? All right, the extinction coefficient we already know because we looked it up, right? And then your path length is 1 if you use the cuvette, 1 centimeter cuvette. Then you just do a basic calculation to determine the concentration. But, you know, you don't want to do just a one-time thing. Maybe you want to definitively show what concentration you have there. So you take multiple readings. So let's say, in this case, you want to make different concentrations of this solution to double check your concentration overall. So you go through and do what is called a serial dilution. So you start from full concentration. You don't do this really on a nanodrop. Don't do this on a nanodrop. Just take multiple readings on the nanodrop. You know, you don't, because path length is small. It's just quick. All right. So if you want to determine like the concentration through like a larger sample with a standard UV vis, you go through and do what's called a serial dilution. So you start at full concentration and you go to 75%, 50%, 25% to 0%. So you're doing several dilutions from your original sample. So you'll take a little bit from there, make 75% of your solution be protein, then the 50% half and half, then you do like a quarter protein of your original solution, you know, and then you'll have like just whatever your solution is. Usually it's like PBS, phosphate buffer solution, when you're dealing with proteins. Tends to be pretty stable in that, so it's all right. So let's say that you run your sample again, looking for the protein to kind of get the patterns. What would that look like? All right, so let's see. So diluting a solution for a nanodrop is like crossing the streams. If you dilute your solution for a nanodrop, you're not going to find any protein. So you're probably not going to find any protein. So you want to take from the original sample if at all possible. You can try to dilute, but you're going to get kind of wonky curves unless you're dealing with an extremely high concentration to start out with. But it's hard to know that until you take an initial reading. So once you get your initial reading, if you got a lot of really crazy large amounts of protein, then you might could do a serial dilution, which I just talked about now. But if you're dealing with like industry and you're in final product phase, then that just means you're going to have to concentrate your solution again later to up the concentration of protein, and that's just a pain because then the more stuff you do to your protein, the more chance you have of losing some of it. And you're dealing with hundreds of thousands of dollars. A little bit stressful, that, you know. So oh goodness. All right, so let's have a look at, let's say you do your serial dilution, and this is what it looks like. All right, you go through and you do your serial dilution. All right, so let's talk about what's in these tubes. All right, so tube 1 is basically just your buffer, your phosphate buffer solution. It has 0% protein, no protein in it, that's it. All right, 2 through 5 have the increasing amounts of protein from 25% concentration to 100%. Now, if you did things right, you should have a steady increasing set of absorbance, and your concentration should go up. So notice here we've got our absorbance here. We shouldn't have anything. So under A, you know, A is our absorbance. Here is our concentration that we determined by plugging absorbance into Beer's law, right? And so what we see here is an increasing amount of concentration. Well, guess what? Our absorbance went up too. So we did this right. Good job, guys. So there we go. So what do we do with that? What can we do math-wise? I'm certain Andy would probably know. That's my dog shaking in the background. I have a really good mic, so if you heard that. So Andy might know about math. We make standard curves, right? What marker is making it red? I don't know right off. I threw this together pretty quickly. So if it's a red solution, what wavelength hits at red? Does anybody know what wavelength hits at red? Red shift, blue shift, you know. So what wavelength hits at red? I just pulled this graphic off the internet because I thought it was pretty useful. I don't know what marker they used in this particular thing. I think it's more of like an educational tool to kind of give you arbitrary, like if this was our wavelength for this particular case. Most of the time, organic solutions tend to be clear. One thing that's pretty interesting that I learned, especially if you have genetic code within a sample, it gets stringy and very snotty. And so if you have nucleic acids in there, any kind of genetic code, it makes little strings, you know. And so it's just like, and it looks weird. I worked with somebody who was like, oh, that's got to be protein. I'm like, yeah, no, it's not. It's pretty stringy and gross. Come to find out, you know, I was right. It's genetic code because that's how it behaves in solution. And I had a massive 260 absorbance. I'm like, there's a lot of DNA in this, or RNA. It's nucleic acids, but it's you got some junk in here. Oh yeah, proteins. Yeah, they're not highly acidic. I was using that image just for a particular, you know, for educational purposes to kind of get us what we should look like. Your solutions may not even have colors. So if you're dealing with proteins, you won't have any colors. No, unless you add some kind of marker that attaches to it. But if you're just looking strictly for concentration, if you're looking strictly at concentration, you won't see colors in there unless you use a particular assay that changes color when it interacts with proteins. So there is an assay just for that, and it's right here in my head. You use BSA normally for it. Bovine serum. And it's escaped me right now. And that's going to bug me all day. Crap. Because you put it in there with the varying concentrations, and you use the same amount, and then you do it with standards, and then you're able to determine how much protein you have on how close it is, and then you stick it into a multi-plate reader, and then it compares the absorbance for those across the board. That's another way to use that. Yeah, it's like a bovine, use bovine serum assay. I guess it is a BSA. Is that it? So yeah, so you can compare the two. Albumin. Oh God, what is that? Bradford's. Frick! It's Bradford's assay. That's what it is. But you use BSA as your protein for your standard curve, and so you put the Bradford's in there, and it interacts with the protein based on concentration. So if you have, like the previous picture, 0%, 25%, 50%, 75%, 100%, and you know what the concentration is of your bovine serum when it interacts with the Bradford reagent, you can put the same Bradford reagent in different dilutions for your protein and compare and see what your concentration is. Bradford's assay. That's what it is. It was right. Thank you, brain. It was right there in my head. So, Bradford's. So, and then you take that plate and you stick it into a UV vis spec, and it blasts it with light, and then it comes back with absorbance and lets you know what those absorbance numbers are, and you can compare them, your particular protein samples, with the standards based on the bovine serum, and you can kind of determine what your concentration is on that. So, what do you do with these numbers? And how do you determine the concentration once you get all of these absorbance sets from your 0, 25, 50, and 75, and 100? What do you do with that? You're like, oh my God, man, I have these numbers. What do I do with these numbers? Well, this is where we get into the portion of this called algebra. You can take this data, plot it on a graph, and determine the concentration based on good old y equals mx plus b. Algebra! You thought you would never use that again. Well, concentrations, when we're dealing with trying to figure out how much a protein is in something, it tends to have a linear curve, meaning a straight line, right? And so if we see these steady increases, we can plot that on a graph, and then we end up with a linear curve. Yep, don't forget your statistical errors when you're graphing your absorption rates right. We can have limit of detection, as well as once you lose linearity. That's something that's important. So when you're graphing your data, when you're getting your concentrations, once you kind of lose linearity and it starts like curving weird to where you don't have a straight line anymore, you have to kind of base your calculations on where the linear curve is. So what does that look like? Let's see what that looks like. Let's see. Here is a graph. Again, something I pulled up off of the internet, right? So here's a graph. Let's say that these were the numbers from our previous picture, and we plot it on an XY axis. We have our absorbance numbers on the Y axis, and we have our concentrations that we mathematically determined on the bottom, right? Through Beer's law. So what you do is you notice, let's see, all these little blue squares are our actual data points, right? So let's say we took 1, 2, 3, 4, 5, 6, 7, 8. Let's say this was our 0% solution, 25, 50, 75, you know, all the way up. So let's say we got really fancy and did multiple concentrations, 7 different multiple concentrations, because we were going to be extremely tedious and picky about our things. So we go back and we get we have our 0%, that's just the saline phosphate buffer solution by itself, and here's our different ones that we did. We did a pretty good job. So what you do is you go in a thing called Excel and you have them find pretty much what your trend line is, and then it gives you an equation. This equation is y equals mx plus b, right? Then you got your r squared value. It's pretty good. This means it's pretty close to the trend line, 0.99. It's pretty close between the two. Now, this little equation right here, this is pretty important because this is going to tell you what your concentration is at any given absorbance. Beer is liquid bread. It's good for you. Oh goodness, once we students had an incredibly flat graph because the student who made the Bradford solution made a math error. It was 10 times the amount of protein it should be. Oh my goodness. Yes, that's not cool. Having more data points is not a bad thing. So how do we use this information then? You're just like, what the heck is this? All right, so remember, absorbance is how strong the sample absorbs the light. All right, so what you do is you pick an absorbance number. All right, that's here on the graph. You plug that in as your y value in your little y equation here, and then you solve the equation for x. X is your concentration. So whatever x equals, that's your concentration. Isn't that fantastic? It's so easy. Hey, the geek room. Oh my goodness, see, it's not so bad. All that high school math comes into play here. It's quite useful, isn't it? All right, so what have we been talking about? We've been talking about spectroscopy. All right, so it's important to note that spectrometers tell you which wavelengths of light were absorbed, and a spectrophotometer measures the intensity of the light that was absorbed or reflected at a particular wavelength. So we're going to look at a box diagram for spectrometers. But why? Because science. So we're going to look at a box diagram. You know, this is highly technical, guys. I don't know if anybody can handle this. Look at that. I have drawn in grad school, I had to draw so many box diagrams for all of the different types of specs, infrared, spectrophotometers. This is a spectrometer. Then when we get into mass spec, that's a whole different ball game. We'll talk a bit about mass spec too, so it's all right. All right. So here we have a spectrometer. All right. So why is this important? I mean, you know, so what's going on here with all these different images? Okay. So essentially, we have our light source, and our light source can vary, and it depends entirely on what type of machine you're looking at and what kind of samples you're looking at. So we'll talk about, you know, light sources essentially are going to change whether you're doing infrared spec or if you're doing UV vis spec. These different types of specs require different light sources because you need intensity at particular wavelengths. That's what it all comes down to, where it lies in the electromagnetic spectrum. All right, so then you blast your light through what's called an entrance slit, and it goes through your dispersion device. Here it looks like a prism. And there's various different ways that you can disperse light into various wavelengths. All right, so it's essentially what we call our monochromator. In these monochromators, you can tweak. Hello, everyone. These monochromators, you can kind of tweak to where they spread the light out, or at least the wavelengths in particular waves. Then you have your exit slit. All right, that's part of your monochromator as well. So that exit slit is going to only allow a particular wavelength out of it. So let's say you're testing for proteins. The wavelength it would let out of the monochromator would be 280 nanometers. That's what it would allow out of the monochromator. Then your sample gets blasted with that particular light, and if it's absorbed, then that's going to show up on the detector as being absorbed at that wavelength. So that's essentially what we're looking at with that. So that's a spectrophotometer box diagram. Now, there will be a quiz at the end. I'm just kidding. I'm not going to do that to you. There is no quiz at the end. If you want, I can give you one. Don't know that you want one, though. You know, so that's okay. All right. So, as I mentioned before, monochromators can be tweaked to be selective to specific wavelengths. The amplifier, if sometimes if you're dealing with spectrophotometers where you want to amplify the intensity of the a wavelength. Now, spectrophotometers, you could have an amplifier there, and that essentially strengthens the signal. One particular amplifier is the photomultiplier tube. That can increase the signal from the solutions by exciting other electrons. And so those electrons get excited, and then it increases your particular signal, and then that way it's easily detected. Light sources I mentioned can vary, and it depends on whether you are using infrared or UV vis. The intensity at specific wavelengths is very important. Infrared has longer wavelengths, while UV vis has shorter ones. Thus, the correct bulb is very, very important. Good thing I haven't covered fluorescence and emission spectrometry. That's fun, too. So not only do, electrons get excited and absorb the light, they also release it, and that's emission spec. So you can actually go and detect what light is being emitted by a sample after it has been blasted with particular wavelengths. You can try to detect those particular wavelengths as they release the light as well. All right. So you can also have a thing called noise. Oh my gosh, why is everything so noisy? Well, noise can affect your solution. Background noise can happen for various reasons. Your sample may not be as pure as you think. So if your noise is as strong as your signal, that's not going to give you a very good reading. You're not going to be able to find it. This is where cleaning up your sample comes into play, but that's another talk. We could get into chromatography, where you have separation of different things in order to clean up your sample. I worked in that as well. protein chromatography through various types of resin. But that's a different talk. But so sometimes your noise, all the things that are in your solution, can set off signals as well. And so if you have that issue, got to clean up your sample a bit. So it's pretty weird. Now let's talk a bit about mass spec. Noise in this case is better defined as signal interference. Yeah, it could be. Mass spec is completely different from spectroscopy. Oh, typical way of telling whether a sample is pure is NMR. Yeah, that's true. So spectroscopy involves electromagnetic radiation, light. Mass spec has nothing to do with light. Now, how it essentially works is that you break apart a compound, and it has highly specific ways that each compound has specific ways that it breaks apart. And so after you've essentially taken your sample and you've broken it up into ions, because you'll pop off different functional groups, so you'll have like a compound. This section will break off, this section will break off, this section might break off. And how those break apart patterns happen in the amount of quantity of each, that lets you know kind of what compound you have. Now, there's different ways, and there's like different fraction patterns. And so a particular compound will tend to have the same fraction pattern each time and how it breaks apart. And it's related to this part only tends to break off this way. Every single time we blast it with some kind of ionizer, where we break apart the compound, this part comes off here, this part comes off here, and this part comes off here. So you can determine what your sample is based on how it breaks apart. That's what mass spec is. Now, it can be, ionization mass spectrometry and tandem mass spec. We have time of flight. We also have quadrupoles. Time of flight essentially is where you break apart your compound, and it's like kind of like a race. And then your heavier portions are going to lag to the back. Your smaller portions are going to move faster. And so the smaller ones will hit sooner than the larger pattern. So that's kind of like time of flight. So how quickly they move across. So I'm going to show you here in just a second a box diagram of a mass spec. So let's have a look at what that looks like. Let's have a look what that looks like. All right, here we go. Here we got a mass spec. So usually we do this with gas because gas is pretty easy to manipulate. So we have at the very beginning, we have our gas sample kind of enters there. Then we have a filament of sorts, and this can vary. You have different ways that you can ionize your compounds. And so when you inject your gas sample into there, your little filament, and again, those vary. You have different ways you can break them apart into ions, will ionize the gas, causing it to break apart in its own type of fractional patterns. And then the ions kind of move towards this little charged slit. Now what happens is this magnetic field can deflect the ions, and it deflects the lightest ones most. So what you end up with, and this is another way that they do this, so the larger ones are not as deflected like the lighter ones are. So the lighter ones end up at this top, and then you have the heavier ones as they move down. So those ions are separated by mass exposed film. So that's kind of what it comes out with. So what does, bye, it was nice having you here if you have to go. So what this essentially does, and what we end up with, is something that looks kind of like this. So this one, let's see, how does that look? All right, there we go. That's good. Okay, I'm not covering up your our spec in the end. So this particular compound is called 4-methyl-3-pentene-2-one. This is the breakup pattern that tends to be exclusive for this compound. Now each number represents how much of the ion is there. So when this particular molecule was broken up, you have like 98, like here, the relative intensity. So the relative intensity goes to 100. Right here, closest to like the mass per charge, all right? So the mass per charge, that's what the m/z is. Here it's going to be, this is your full unbroken molecule. This little red all the way to the right here is your full unbroken molecule. This here, the amount of mass that you have here, this is 98. You have a pretty high amount, about 60, close to 60 intensity. I think maybe 55. So we have about 98 here. So that's the amount of mass. So 83, 55, 43, 39, 29. So how it breaks apart is extremely important, and that lets you kind of know essentially what the compound is. Now, I had qualifying exams on this, and it was primarily on the database associated with mass spec. There is a giant database to where if you were to run a mass spec and get a pattern like that, you could compare it to other known compounds to kind of figure out which one is. Sometimes they're closely related to one another, so it's not exact. So sometimes it's not exact, and it's not a full bang-on thing. There's still a lot of work that needs to be done on cleaning up the mass spec database, but it's a good starting point, especially if you're dealing with a sample and you don't know what's in it. Now, the other thing, you could run a spectroscopy like UV vis, infrared, whatever, on your sample prior to and your sample afterwards. This is really good at helping you determine what your functional groups are. Make sure you don't get ants in your sample. So this can also let you know what kind of functional groups are. And you can run what's called an NMR. Somebody mentioned that before. Nuclear magnetic resonance. And let you know kind of what you're dealing with if you have an unknown sample. So spectroscopy is good if you have a general idea of what it is that's in your sample, if it's proteins, if it's DNA. But if you don't know what's in it, sometimes it's good to start with a mass spec. Get a general idea and say, okay, this is how the fraction patterns are for this particular compound. We're getting one here. We have, this breaks up here. And so and there's like double bonded carbons tend to have a fraction pattern, this sort of thing. Same with NMRs. They show up very regularly in the same types of patterns. So it's good to just compare. So you run your mass spec, you compare it with known data, and then it gives you an idea. Then you can go, oh, I'm dealing with a protein. Woohoo! I can run it at 280. But it looks, maybe it's nucleic acid. And run it at 260. See how much is there. So it's all part of a process. But a lot of people get mass spec mixed up with UV vis spec, and it's not the same. They're completely different. And you're measuring completely different things. You're literally measuring the mass of a molecule with a mass spec. And the parts that are broken apart, it tells you how much the mass is. So, hey, Monty. So that's what we're dealing with when we're dealing with mass spec versus like spectroscopy. So, while Andy and Monty is here, when will our phones be able to do spectroscopy? I don't know, man. We got good microscopes on there. We could do that, We could probably be easier to detect fluorescence. Because if you're getting in like UV vis stuff, I don't know, man. Maybe that's something I need to work on. That'd be kind of neat, wouldn't it? So, while Monty and Andy are here, in a few weeks, I will be in New Orleans. I mentioned this at the beginning of the broadcast. We will be talking about the first licensed pharmacist and the pharmacy museum that is in New Orleans on Spirited Science. That is going to be the 19th of January. So 2 weeks from today, we will have a return of Spirited Science where we will be talking about the first licensed pharmacist, pharmacy museum, and eugenics practices that were going on in Louisiana and some of the lore that's associated with that's become part of their cultural history. And so Monty, Andy, and myself We'll be knocking that out of the park. We'll be knocking that out of the park on the 19th. Then on the 24th, I will have my very first episode with Katie Paulson from Pathos called This Week in BS. This Week in Bad Science, where we'll talk about the latest and greatest in death dealers, homeopathy, trends, fads, stupid things celebrities do, mixed bag of all kinds of stuff. So that's coming up. Next Saturday, we will be talking about life on outside of Earth. Is it possible? What's going on with that? So that'll be pretty cool. So that'll be awesome. We'll be hanging with Monty in a couple weeks. Me, Andy DeWitt, and Monty Stickman. Check out Monty's show, Hannibal and Monty's Shit Show. I said a dirty word on here. I appear on their show every week with a little bit of science. This past Thursday, we talked about the metric system, RARs and laws. You know, hopefully this show's been kind of like decalaws, maybe a little bit. You know, decalaws. Laws being funny, a unit of funny, RAR being a unit of sexy. So, I guess we should talk about everything that we talked about today. And then we can have a little chat at the end. All right, so we have talked about types of spectroscopy, how it works, the difference between it and mass spec, all of the differences associated with that. So, centilols. Oh, yes. Thank you, Hemp Hill. He's going to send me pictures from the Pharmacy Museum. Thank you. All right. So we've talked about the types of spectroscopy, how it works. If you missed some of that, you can always go back and rewatch. I also have an episode where I talked about nanoparticles, plasma and resonance, that sort of thing, which was relevant to this with our IR discussion. And I did do a whole episode just on photons and the electromagnetic spectrum. If you want to dive more into that, that'd be pretty cool. I bring the kilo laws. So I'm going to take a minute to thank all of my patrons. Thank you, James, Jen, Carl, Melanie, Patrick, Daniel, Stephen, Paula, Carrie, Cersei, Keith, Duke, James, Andy, Zachary, Tony, Bo, Stephen, Sarah, Chris, Graham, Dragnot, Godless Iowan, Jennifer, Richard, Dark, Fearsome, and Neil. Thank you so much. I think Richard. Yeah, I did put Richard on here. Yay! I didn't leave off Richard. I want to thank you all for being part of my Patreon, patreon.com/ScientistMel. I don't think people realize the amount of expense that goes into what I do to upkeep my website. I also pay for advertising to boost that scientific literacy. They help me keep the lights on. They help me be able to stream to multiple platforms. I also have a new camera, so I'm going to be making short films again and editing more science content, not live streaming, but more time editing actual shows. So that'll be really cool. So thank you guys for contributing. Also, if you're a higher paying patron, you get artwork. You just need to let me know what image you want. Recently, Chaos Theory was uploaded. Took about a month for that to be drawn. That's from Livid Unum. And so if you like that piece and you're a higher paying patron, I will print that out and send it to you, and you'll have your own special edition piece. That is for you guys. You can find me everywhere on the internet, ScientistMel.com, Patreon.com, Periscope, YouTube, Facebook. I'm also on Twitch, streaming there now. And I will be doing the 24/7 live stream. I'm going to update with new episodes, and that will start up again on Sunday. Only short films. I'm hoping to do other things too. So if you got questions, I got a few minutes to where we can like chat a bit. Well, I would like to do full-length films, but unfortunately, full-length films are not conceivable right now. It would take a little while. So yeah, so it'd be pretty cool. I'm checking out some stuff for Kids DIY Optical Science on Twitter. Also, Sunday Science will be on my channel for Andy until everything gets sorted out with SciStrike's channel. And so look for Sunday Science. When we get that together, I'm going to host that on my channel for a little while until Andy transitions to his. And so that'll help out a bit. Um, so do check that out. So Sunday Science has me, Strike, Stephen Bauman, and Andy. It's Andy's show, and so I'll be hosting that a bit on my channel until he transitions to his. So that'll be really awesome. So guys, remember, you can always send me your topics. All of my topics are viewer generated. All of my polls are voted by everyone. They all pick what it is I talk about. I just put it together. I have my list. I actually have a handwritten list of stuff, you know, from people. I'm like, okay, inflationary universe. That's going to be on one soon for a poll. Human sexuality was put on there. Addiction, I think. Now, I did talk about diets. I can't read my own writing here. I legit cannot read my own writing. So that's a problem. Sonoluminescence. Sonoluminescence. I will write that down and shoot that to me in the comments. If you have anything that you want me to talk about, put it in the comments too, and that will help me, and I'll be able to throw that in on my polls. I'll be doing more polls on YouTube as well. My polls tend to be on Twitter, but I'll post them on YouTube as well. Yeah, I'm not certain what I wrote really fast. Somebody gave me a topic, and this is why I say put it in the comments, because my handwriting's horrible. Well, thank you for being here. We've been on for an hour now. This is pretty cool. I love chatting with you guys and interacting with you. So look for the new shows this week in BS. That's going to be awesome. This week in BS. Also, Revival of Spirited Science. We already have the cocktail made. It's called The Pharmacist. And so I'll make the recipe. And so you guys can share in the adult beverage. You can also choose non-alcoholic beverages. You don't have to drink to be part of the show. I want to make that clear. You can just sit around, have a soda, tea, water, whatever you drink, and hang with us while we talk about sciencey stuff. Aw, Monty is awesome too. And I should say Monty designed my original logo, the Science of. So cred to Monty for that, for making my original logo. He was the first person that contributed to my work. Thank you, Monty. Oh my goodness. I should see your handwriting. Oh my goodness. Thank you, Bo. Well, I'm going to hop off of here because I'm going to go see Aquaman today in the IMAX. Woohoo! I want to see Aquaman today. For those doing dry January, absolutely. If you're doing dry January, you are never required to imbibe alcohol in any way, capacity, or form. I just put the recipe out there in the event people want to. But it is never a requirement to hang with us and join us for Spirited Science. So we just want you to learn and have a good time and embrace scientific literacy. So I will see you guys later. I'll let you know what I think. But I'm going to end it with Mr. Rogers, man. You always make each day special for me. You know how? By gesture being you. Sending you squishy science hugs and loads of kisses. Have a fantastic Saturday. And thank you for being here. And that has been the Science of Spectroscopy. You guys are awesome. And I will see you guys later.